Well, good afternoon, good evening, everyone, and welcome to SETI Live. My name is Simon Steele. I'm the Director of Education and Outreach at the SETI Institute, and we are going to be looking at an amazing discovery by the TESS satellite of a sextuplet star system. And to tell us more about this is one of the co-discoverers of this system, Veselin Kostov, who is a SETI Institute astrophysicist who's based over on the East Coast at the Goddard Space Flight Center. And what I want to start off thinking about, Veselin, is that we are orbiting a star that happens to be all alone by itself. A lot of stars in the galaxy, in fact, probably about half the stars in the galaxy are actually binary systems or multiple systems. Even our closest neighbor, Alpha Centauri, is a triple star system. And so, having multiple star systems is not unusual. Did this one with six take everyone by surprise?
Good question. It took me by surprise, but I'm not a stellar astrophysicist by training. It is not the first sextuple system, so from that regard, it's not unique. What makes it unique is the eclipses that we see from every pair, from all three pairs, all three constituent pairs of eclipsing binaries.
Okay, so it's the eclipsing aspect, and of course this is yes, where TESS comes in, and TESS wasn't designed. Well, it's designed for this, but it's not the primary mission. Could you say a little bit about the TESS mission?
Yeah, so TESS is a spacecraft launched maybe 2 years ago or so, 2.5 years ago. Time flies; it's easy to forget. And the primary goal of TESS is to find the transiting exoplanets, especially those that orbit nearby stars, bright nearby stars, that are probably the best targets for follow-up observations that might help us characterize these potential planets beyond, sizes, beyond radii. Mm-hmm. Hopefully masses, and ideally maybe potentially even some hints for atmosphere, for the presence of atmospheres around them. But to do this, we need to find the planets orbiting the brightest nearby stars available.
Right. And just to invite everyone, please do let us know where you're watching in from, where in the world you are. And also, if you have any questions, we'll turn over the questioning to you all in the audience about halfway through this broadcast. So please do pop up your questions if you have any questions for Veselin. So TESS, as you say, is sort of like Kepler before. It was designed to look for variations in brightness of stars that may be indicative of a planet passing in front of that star, and therefore you discover the planet by virtue of the brightness variation in the star. But of course, any eclipsing system will give this process, and that's how you discover, get more information about binary or multiple star systems too.
Yeah, exactly. When you're hunting for transiting planets, it is very easy to catch an eclipsing binary. In fact, so easy that you catch more eclipsing binaries than transiting planets, which is a problem because based on the photometry alone, based on the data from TESS alone, it is not trivial to figure out whether what you're seeing is a transiting planet or an eclipsing binary.
Right, right.
And this becomes a real issue when you're looking at tens of thousands to hundreds of thousands of potential targets,
Yeah. So this one came up, and this has the exciting name of TYC 7037-89-1. What do those letters and numbers mean?
So TIC, this means TESS Input Catalog. This is a catalog of stars observed by TESS. It is a conglomerate of many prior observations and catalogs, and it is trying to provide as much information, as much available information on every star that TESS observes as possible. Mm-hmm, mm-hmm. And the number is just a number.
Just a number.
Yeah.
Yeah. One day maybe get a real name.
Well, I mean, all these stars already have names, or the vast majority of these stars already have, if not names, then at least prior catalog numbers, catalog identifications.
Right.
So yeah, it is known as TIC something 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 from TESS, but it has probably half a dozen other names from previous catalogs.
Right. Yes, true. A lot of astronomical objects have multiple, sort of pseudonyms, don't they? And certainly galaxies or nebulae, whether they're part of the Messier catalog or NGCs, depending on what observatory observes them, they get multiple names.
Exactly. People have been looking at the sky for a long, long time, and we tend to name things that we see.
Yes. So we already have people tuning in from Montreal, from Denmark, Indiana, Dublin. So welcome everyone to tuning in from around the world. That's fabulous. So this star was known before TESS. This wasn't this object in the sky or set of objects was known. And then you look at this system with a telescope, and you're seeing multiple dimmings and brightenings and everything. How does this basically each star is a pixel. It's not any bigger than that. How do you do the analysis to turn this varying pixel into a multiple star system?
Yeah, so that's a great question, and it's a question I love talking about because it really gets into the details of how science is done. Because there is a very large and long process between what you see, let's say, in the news, and actually where this all starts. So yes, TESS observes the entire sky. TESS monitors the entire sky and measures the brightness of tens of millions of stars spread across the entire sky for at least 30 days. So each star is observed for at least 30 days, every 30 minutes. So you can imagine the amount of data this is. This is called photometry. Photometry is basically brightness of a star as a function of time. So this particular target, TESS observed it every 30 minutes for actually 60 days. In this case, it was observed twice in so-called two sectors. And this TESS measures the brightness of the star. If there are eclipses or occultations on that star or in or around that star, the instrument detects decrease in the brightness. When something blocks something else, you're losing some amount of light. For example, if the amount of light that you receive from the star outside of any eclipses is, let's say, 1, when an eclipse occurs, you're losing, let's say, 10% of the light, and TESS detects this. So over the course of a few hours, the brightness of the star, as measured by TESS, decreases by 10, 15, 20, 50%, and then it goes back to the baseline flux of 1. And the instrument measured multiple dimmings in the brightness of this star, which were actually, the dimmings were significant enough that this kind of immediately indicated that what is blocking the light is not a planet. It is too big for a planet to produce so much dimming. So this was immediately obvious that these are stars blocking each other's light. And when you start looking at the signal, at the timing component of this signal, you actually notice that first there are 3 distinct signals on 3 distinct periods, on 3 periods unrelated to each other. So this means that what TESS sees as a single pixel, there is a star in there, and there are at least 3 pairs of stars in there producing periodic dimmings.
Right.
At different periods and different dimming depth.
Yeah.
It all depends on the individual configuration of the individual system.
Right. So it's almost like, one star passing in front of another is a very repeatable pattern. And then you've got a second set of stars going, overlapping each other, another set. And so it's sort of like, the difference between a single musical tone and an orchestra playing. You've got all of these notes, all these different frequencies of dimmings and brightenings going on all the time. And somehow you need to pick those apart.
Exactly.
Yeah.
Exactly.
I'm going to share the image of the system now. Now, this is, as we know, is an artist's conception of the system, because all of this is crammed into one pixel in the detector. But here, what has emerged from this analysis is this incredibly complex dance. You know, it's a waltz of stars, isn't it, in a way? Is this something you could do by a human eye, or is this something that you have to get a serious number crunching going?
You mean to produce the figure, or to figure out the system?
To figure out the system.
So yes and no. Yes, because as you mentioned, this is the signal is basically a clock. There is a clock ticking in the data, and in this case, there are three different clocks ticking at 3 different intervals. So a human eye can. It's difficult, but you can kind of pick this out by eye. Actually, that's how we figured it out initially. We figured it out. You know, we were putting horizontal bars between the different eclipses, and we're like, oh yeah, we need more than one. We need more than 2. So we need 3 different lengths. This is extremely rudimentary because we were just starting to look into this. Of course, there are established algorithms and codes that are designed to do this kind of work. But you know, the first, let's say, half an hour of excitement, you do the most basic things. So the human eye can pick out the distinctiveness between the 3 signals, and then you can immediately measure the orbital period directly from the data. You need no machines to measure the orbital period. Yeah, it's not going to be very precise, but it will be precise enough. And so this was part of the answer why I said yes. The reason I said no is because in some systems, and in this particular system, if you look at the subsystems that we call A and C, so system A and system C. So as I mentioned, the thing that we measure directly from the data are the orbital periods. So we can see the 1.3-day orbital period, the 1.6-day orbital period, and the 8.2-day orbital period. This is clear in the data. This comes out immediately from the data. What is not so obvious, and actually what requires number crunching, is these 1.3 and 1.6 days orbital periods, they are in fact not constant. So there is a very slight shift in both of these periods, a very slight. You really do need a machine to figure this shift here. And this shift is caused by the gravitational perturbation from one system onto the other. So in fact, systems A and C are close enough to each other that they perturb each other's strictly periodic orbital periods. And this is actually why we know that A and C are separated by about 4 years of orbital period. Here I have an orbital period of 4 years. We actually see hints of a long-term, in this case, a 4-year long-term trend in the orbital periods of A, and exactly the same trend in the orbital periods of C. It's exactly the same time scale, but it's different. It's the opposite direction. And this immediately tells us that these 2 systems actually push and pull on each other significantly, that we detect this signal in the data.
Right. And if we just look at this system, and this is not to scale at all, and in fact, it's not even oriented correctly, because of course these stars were discovered by an eclipsing process. So we should be sitting in the plane, lining up with all of these. So although it's a nice diagram, it's completely unrealistic at many levels. But so we should put that out, straight away.
Right.
But if we look at the separate, the orbital separation of the A system and the C system in themselves, with a 1.3-day orbit. Now it takes the Earth a year to go around the Sun at a distance of 150 million kilometers. So these systems in themselves are very, very tightly spaced, aren't they? I mean, these stars are really whizzing around each other.
Extremely tight, yes.
Yeah.
Yes.
And even A and C, the A system and the C system, which are orbiting around their center of gravity, just like any pair of masses, every 4 years, that's still pretty close, isn't it? How big is that relative to our solar system? in terms of scale?
Yeah, I was just about to look this up.
Okay, sorry to throw that.
No, that's a great question.
Yeah.
So it's about half an astronomical unit, actually.
Okay, so half the average separation of the Earth to the Sun, the two binary systems. So when you think that's a lot of stars in a very small area volume of space, isn't it?
Yes.
That's going on there, which is amazing.
Wait, I think I got this wrong. Let me get back to you on that.
Yes,
but...
no, fine. but whatever value it is, these are tightly packed. And then you've got the B system, which is way out there with a 2,000-year orbit. So this will, obviously, it'll be an interesting effect when this, swings, more closely to the other two systems. But that's it's quite dramatic. And as you say, all these stars are gravitationally interacting with each other as masses do. Is this
only the A and the C pair? Only they're close enough. B is too far away. Yeah.
Too far away, right?
Yeah.
How stable is this? It looks though it's something, it's like spinning plates. You can set this system up, and is this a long-term stability that you've got here?
Yeah, so it should be pretty stable because, as you mentioned, the individual A and C systems, they're very tight. They're one-day orbital period. So the separation between the A and the C system is hundreds of times larger than the separation between each of the stars.
Right.
So these should be long-term stable.
Okay.
And I just want to mention another thing, which is also interesting, and the fact that can I go back to the diagram?
Sure. Yes. Yeah. if I can find it, hang on a second.
So the fact that we know that this is a sextuple system. When you say a sextuple system, this means that you have good indications that everything is bound to everything else. So we do see that A and C are close enough to perturb each other, which means that they orbit each other. We cannot see this perturbation due to B because, as you mentioned, B is too far away and it will take thousands of years to see any signal. But what we do see is we can actually resolve as distinct sources, resolve on the sky as distinct sources B and A plus C. So we see where there is where it looks like there is one star on the sky, we actually see two sources. One of the sources is the B system, and the other source is the A and C combined.
So for low resolution, it looks like a binary system. But when you look in, that binary system then turns into this multiple system. It's like sort of at a distance, you see a car coming down the highway from a great distance away. It just looks like one light, and then as it gets closer, you can resolve two headlights. And so this, with the resolution, you've now broken that down into six. Yeah.
And even beyond that, so we observed the system with spectroscopic instruments to measure how the individual spectra of each star shifts left and right due to their individual Doppler shifts. And actually what we do see, so we resolve 6 individual spectra in the data itself. And we see these spectra moving left and right in wavelength space as according to the 3 orbital periods. And on top of this, we see that so these 6 spectra, they move left and right, but they don't move around 0. They move around the velocity of each system, the 3-dimensional velocity of each system from our perspective, as measured from our perspective. So actually, we see that the so-called radial velocity of the B system is basically the same as the orbital velocity of the A and C system. So this means that B and A plus C are moving, they're at the same place on the sky, and they're moving in the same direction on the sky from our perspective.
Right.
So this gives us confidence that this is likely a bound system. That there is a very small probability that these are just chance alignment between so many stars in so little space.
There's so little space. And of course, they are, this system is orbiting the center of the Milky Way, just as we're orbiting the center of the Milky Way. Yeah,
absolutely.
Yeah. So we got a few people. I just want to call out to a few people. watching in from Denmark, from Buffalo, New York, Arizona, Plymouth in the UK, St. John, Brunswick, Canada, Redding, California. We've also had a couple of star donations. Thank you to Sabine. Thank you to Clenio, hope I'm pronouncing your names right, for your star donations. And thank you to Paul, who has donated $250 to the SETI Institute. We, as you all know, I'm sure the SETI Institute is a non-profit organization, and we rely both on NASA and government federal funding, but also on the donations of viewers like you. So thank you so much, both for watching and for your donations. Just a little bit about these stars, because on the diagram, a couple. 3 of them are drawn sort of smaller and redder, 3 of them are drawn bigger and whiter. How do these stars in themselves compare to the sun?
So the whiter ones, the bigger ones, are slightly bigger, and the yellow ones are very similar to the sun itself.
Okay.
So the bigger the whiter stars are maybe 20% larger, more massive, and the yellow ones are maybe 50 to 60% of the mass of the sun. So they're on either side of the sun, basically.
Okay, so the sun, if on this diagram, would be somewhere in the middle in terms of size and brightness. Okay. Yes. We have some questions coming in. One of the questions again is about scale. How big is this B system orbit? 2,000 years. That's a very large orbit when you think that compared to the planets of our solar system. This is a big distance.
Yes. I don't know the number on top of my head, but we can all use Kepler's equation. We know the masses and we know the orbital period, so we can just plug it in the Kepler equation and figure out the size.
Yes, and that's the amazing thing. That always amazes me, that Kepler's laws, developed by Johannes Kepler, hold for our solar system, developed for our solar system, and yet it works for anything orbiting anything else, really, which is absolutely amazing. Whether it's multiple star systems, whether it's stars orbiting the black hole at the center of our galaxy, it just shows the universality of the laws. It's brilliant. So we've got Kepler. I'm going back to a different telescope now. TESS was designed to find exoplanets, and now it's coming up with all these magnificent systems. And I'm surprised there haven't been questions on this yet, because it intrigues me. Would it be possible for a planetary system to exist on anywhere in this? How would you have a planet, and what would it be like?
So I doubt there is much room for a planet to be in the AC system. The 2 binaries are, I think, they're pretty close, 4-year orbital periods. There isn't much, if any, room for dynamical stability, for dynamically stable orbits. I may be wrong, but I don't think I'm too wrong on this. I would be. Let me put it this way: I would be surprised if there are any planets in the AC system.
Okay. Yeah.
The B system, the one that's 2,000 years away, it is very isolated from the A and C, and it can perfectly well harbor planets around it, not inside, not in between the 2 stars, but around the 2 stars.
Right. So if you're far away from this binary star system, then as far as your planet's concerned, it's just a central mass. It doesn't matter if it's 2 binary systems. So
well, you cannot get too close. There is certain distance below which a planet cannot survive. But beyond ballpark 5 times the separation of the binary star itself, you're perfectly fine.
Right. So who knows?
Who knows? Yeah.
Who knows? That will be quite an exciting discovery.
Yeah.
Another question coming in. Would it be possible to detect properties such as this in a system with an orbital plane not aligned? So obviously this was discovered because we have this alignment that allows for transits. If we were looking at a star, out in the night sky that say it was the plane was at 90 degrees to our view, or some angle in between, how would you actually look at that and try and find out what's going on and whether that's another multiple system?
Yeah, that's a good question, and it actually feeds back into what I mentioned at the beginning. What makes this system unique is really the eclipses, because as you mentioned, you can have a face-on orientation on the sky of two stars, and you can probably figure out that they make a binary system if you observe long enough and if you see their mutual orbits. However, unless you get eclipses, unless you see eclipses, it is difficult to have precise measurements on the stellar sizes. And the sizes and the masses and the temperatures of the stars are the fundamental building blocks of the entire stellar astrophysics. So if you can only measure directly from your observations the masses, you're still missing basically 2/3 of the information that you need to characterize the system itself. So this is what makes eclipses extremely valuable, because they give you the complete solution of the system. This is the beauty of eclipsing binaries. And
yeah, and the fact that this is a chance alignment, which is chance in terms of our location compared with this system's location, and yet we are discovering through this eclipsing these transits so many planetary systems as well. That implies there are many more times as many planetary systems that we cannot detect simply because the orbital alignment's not right.
Absolutely. But basically, for kind of the running joke in the field is, for everyone that we discover, there are thousands out there that we cannot. Just because they're not transiting. There are other ways to detect them, but you will never see them in transit.
So what's the future now for your work and for TESS? I mean, this is very exciting. Does it fit into a larger plan to see how many stars you can get, or in orbit around each other? Is there a race or a prize for the next one? No, I found 8. I found 12.
Yeah, good question. I think we got lucky with this one because we kind of discovered it very early. But actually, the purpose of the half of our project, half of the projects that we work on are focused on just 2 stars, on just a plain boring eclipsing binary, because there are for the first time we have the opportunity to measure the brightness of hundreds of thousands of eclipsing binaries spread across the entire sky with space-based photometry, with space-based photometric quality for, as I mentioned, at least 30 days. This was never possible before. This is a homogeneous data set of eclipsing binary stars that is unique. It's yet another unique thing from TESS. And as I mentioned, these are the building blocks of stellar astrophysics. So part of our plan is to really focus on the detailed science of hundreds of thousands of eclipsing binaries observed from TESS. So just 2 stars. Some of them will be higher order, triples and quadruples. But the main focus will be on the eclipsing binaries themselves.
Right. Now, stars are born in clusters. Is it probable that this system was born as a family, out of the original sort of nebula, or do you think this is a system that maybe, especially the outermost pair, is this something that could have been captured? How does the evolution of this or the birth of this system look like?
I guess this is the $1 million question for this case. And our current hypothesis, which is, of course, one of many, is that initially there was a pair of stars. So initially there was a simple binary system, a binary system that captured a 3rd star on a much longer orbit. And then subsequently, each of these 3 stars fragmented into 2. So you start with 2, you capture a 3rd one, and then each of these fragment into 2. and you come up with this 2 plus 2 plus an outer 2 configuration. But this is our best guess. Again, it is one of many potential options, and with one data point, it's practically impossible to say anything with 100% confidence.
Sure. You just need to keep looking to find more of these crazy systems out there. Yeah.
Exactly.
Yeah.
If we keep seeing the same configuration, that it will mean that it's very likely, But if we see completely different configurations, it means that there is an enormous amount of diversity in these systems.
Wonderful. I do have to give a call out for some other SETI events coming up. We have SETI Talks next week. Strange and Intriguing Exoplanets is the subject, and you can find out much more about that talk on our website. Please do go to our website to find more about Veselin's work as well. We have a couple of pages that go into this discovery in more detail. We also, next Thursday, of course, moving to a smaller scale, we have a Mars lander. Perseverance will be arriving at Mars and touching down softly, we hope. And we are having a watch party at the SETI Institute with a panel of special guests. So please do tune into that. And again, all the details of this is on our website. So Veselin, I'd like to thank you very much for talking about this amazing system. It just shows that the more you look into the universe, the more you discover, and these things just come out of nowhere, and it's just amazing what nature can throw at us.
Absolutely, and thanks for having me. It's a pleasure to be here.
It's been great, and thank you everybody else for watching, and tune in next week for another SETI Live. Thank you very much.